Welcome to today's Explainer. Today, we're doing something really cool. We're bridging the gap between everyday macro-level phenomena and the microscopic quantum world. We're going to figure out exactly how heat physically alters the materials all around us.
I mean, just think back to the dramatic train derailment in New Jersey back in 1978. Unseasonably high temperatures caused solid steel rails to expand so much that they literally violently warped right out of their straight paths. It's a stark reminder of the immense, destructive power of unanticipated heat.
But, we can actually harness that exact same power for good. By bonding together two different metals that expand at different rates when heated, we create a bimetallic strip. As the temperature changes, the strip bends, and that bending tilts a little glass bulb of mercury to make or break an electrical connection. It's brilliant! This is the ingenious heart of the mechanical thermostats that regulate our homes.
To truly grasp how all this works, our explainer today is going to cross a sort of macro bridge. We're covering the power of heat capacity in phonons, the mechanics of thermal expansion, how materials conduct heat, and finally, surviving thermal stress. All right, let's kick things off with part 1, the power of heat, from phenomena to physics. So, when a solid absorbs thermal energy, its temperature rises, right? And its dimensions increase. We measure a material's unique ability to take in this energy through a property called heat capacity. It's basically just the ratio of the energy gained to the resulting temperature change. Simple enough. But to understand where that heat actually goes, we need to zoom in.
And that brings us to Section 2, Heat Capacity and Phonons, the invisible dancers. How exactly does a solid store this heat energy at the microscopic level?
Well, atoms in a solid aren't just sitting there static. They're vibrating at incredibly high frequencies. And because these atoms are bonded together, their vibrations aren't independent. They coordinate into traveling elastic waves, which are essentially sound waves propagating through the crystal lattice. And since physics is awesome, only certain energy values for these waves are allowed. The energy is quantized. A single quantized unit of this vibrational energy is what we call a phonon.
Now think about how heat capacity behaves as the temperature shifts. Down at absolute zero, heat capacity is zero. As the temperature rises, it shoots up rapidly because the lattice waves have a greater ability to boost their average energy. But it doesn't just go up forever. It eventually levels off at what we call the Debye temperature. Above that specific point, even though the material is getting hotter and total energy is increasing, the actual amount of energy required to raise the temperature by just 1 more degree stays completely constant.
Moving on to Section 3, Mechanics of Thermal Expansion, Changing Shape. Because as materials absorb these phonons, they don't just heat up, they physically change their shape.
So why do things actually expand? The secret is in the atomic bonding, specifically an asymmetric potential energy trough. Picture atoms resting at the very bottom of this trough at 0 Kelvin. As they heat up and gain vibrational energy, they start oscillating higher up the sides of the trough. Because the right side of this curve sweeps outward, the average position between the atoms, their mean interatomic distance, gets pushed further and further apart. To really grasp why that asymmetry matters, just consider the exact opposite. If the atomic bonding curve were perfectly symmetric, the atoms would still vibrate wider and wider, sure, but their average center position, it would never shift. Heating wouldn't change the net distance between atoms at all, meaning you'd get zero absolute macroscopic expansion. Kind of mind-blowing when you think about it.
When we look at linear coefficients of thermal expansion, standard metals like copper and iron obviously expand quite a bit. But then there's INVAR. Back in 1896, Charles Edouard Guillaume actually won a Nobel Prize for discovering this specific magnetic iron-nickel alloy. As INVAR heats up, its normal tendency to expand is perfectly counteracted by a contraction phenomenon tied to its ferromagnetic properties. The result? A near-zero expansion coefficient. It's a total game-changer for things like precision clocks and lasers, where even a microscopic shift ruins the whole shebang.
Before we jump to the next part, chew on this everyday mystery. You walk out to your car on a freezing winter morning. The metal door handle feels incredibly cold, right? But the plastic steering wheel inside feels totally fine. They've both been sitting in the same freezing air all night. They're at the exact same temperature. So why the huge difference in how they feel?
The answer lies in Section 4, How Materials Conduct Heat, Electrons versus Phonons. This is all about how heat moves through different materials.
At its core, thermal conductivity is simply a measure of how efficiently heat gets transported from a hot region to a cold region within a substance. Heat is always going to flow down the temperature gradient, but the actual mechanism pulling that off, that depends entirely on the material.
And this contrast perfectly solves our cold car mystery. Metals have this vast sea of highly mobile free electrons. So when you touch that freezing metal handle, those fast free electrons rapidly suck the thermal kinetic energy right out of your warm hand and carry it away into the metal. The plastic steering wheel, on the other hand, is a polymer. It doesn't have free electrons. It has to rely on the much slower, far less efficient domino effect of phonons, those lattice vibrations we talked about, to move heat. Because it transfers heat away from your hands so slowly, it just doesn't feel nearly as cold.
All right, that brings us to our final section, Section 5, Surviving Thermal Stress, the breaking point. This is where we tackle a massive macro-level engineering challenge, dealing with the destructive forces of restrained thermal expansion.
You remember those buckled train tracks from the beginning? Well, if you lock a material in place and heat it up, it physically cannot expand freely. Instead, massive thermal stresses build up inside it. And get this, it's the exact same amount of stress that would be required to elastically compress that material right back to its original length.
Now, for ductile materials like metals, they might just bend or warp under that stress. But for non-ductile, brittle materials like ceramics, rapid cooling is a total nightmare. The exterior shrinks super fast while the hot interior resists. This creates enormous tensile stresses on the surface, literally pulling the material apart. Since ceramics can't stretch or deform to alleviate that tension, cracks propagate instantly and the whole piece shatters. This is the phenomenon known as thermal shock.
So how do engineers combat this? By chemically altering a material's properties to lower its expansion rate. Take standard soda-lime glass, for example. It has a high expansion coefficient and shatters super easily under rapid temperature changes. But by adding boron to the mix, engineers created borosilicate glass. You probably know it as Pyrex. Its expansion coefficient is roughly 3 times lower, which drastically reduces those internal stresses and ensures your baking dishes don't explode when you yank them out of a hot oven.
From shattered baking dishes to buckled railways, all the way down to the atomic potential energy troughs shaping our physical reality, heat absolutely changes everything. By understanding these microscopic phonons and electrons, we can actually engineer our way around these destructive forces. But as our technology pushes into deeper space and faster computing, forcing us into hotter and far more constrained environments, you really have to wonder, how will we engineer the thermal materials of the future? And what new invisible dancers will we need to tame next? Thanks so much for joining me on this explainer. Keep learning, and I'll catch you next time.